So I want to give an example of how we can use these Taylor series in order to actually approximate these functions. Specifically, I want to look at an example that will, be relevant to statistics. Specifically, this e to the x one that I talked about here. So let's look at this statistics example here. Okay. So let's let x be a standard normal random variable. And I won't get into all the definitions about random variables and all that because it's not really important to what we're doing here. But this is how it would be presented, right? So then this means that the probability distribution function of x here would be f of x is equal to 1 over the square root of 2 pi e to the negative x squared over 2. So this negative x squared over 2 is very hard to integrate. And we need to integrate in order to solve probability questions. So what if we want to find, well, rather here we're going to approximate. So let me say to approximate the probability that x is between -1 and 1. Okay. Then this would be the integral from -1 to 1 of f of x dx. Okay, this is the definition of a continuous random variable, the probability on an interval of a continuous random variable. But this is very difficult to do. And when I say difficult, I mean impossible to do by hand. This function is not able to be defined in terms of elementary functions. Elementary functions are the trig functions, e to the x, natural log of x, polynomials, all the ones that we know. I don't want to say impossible. You can get an answer using some more advanced techniques for the definite integral case, at least, but the indefinite integral has no elementary antiderivative, meaning, again, it can't be written in terms of those common functions. So this is where an approximation might be in order. Okay. So we know that e to the negative x squared over 2, we can include this part too here. This would be equal to the sum from n equals 0 to infinity of negative x squared over 2 to the n over n factorial. Okay. So we can simplify this a bit here. So we'll get n equals 0 to infinity of -1 to the n x to the 2n over 2 to the n times n factorial. Okay, this would give us, this is probably the simplest form we can put it in here. So we would want to decide how many terms we want here. And there's not really a good answer to that. I'll just do like 3, just so we can kind of see where it's going. So let's look at the sum, the first 3 terms of this. So let's say this is approximately 1 over root 2 pi. And then we're just going to look at the first 3 terms. So we're going to put in n equals 0. So it'll be positive, and then it'll just be 1/2. No, just 1, right? Because this is 1, this is 1, this is 1. And then we'll put in 1, so we'll have negative x squared over 2, right? And then we'll add we're putting in n equals 2, so this is going to be x to the 4th over 4 times 2, so 8. Okay. And I guess we can do one more term because that doesn't seem sufficient. So we'll put in n equals 3, so that's x to the 6th. This is 2 to the 3rd, which is 8, times 3 factorial, which is 6. So 8 times 6, so it's going to be 40. 8, right? So this is the first 4 terms here. So let's just use this for our integral. One thing to note with the normal distribution, just to make it a little bit easier here, is that this is equal to 2 times this, because the normal distribution is symmetric around the mean. The mean here is given to be 0. So just to make it a little bit simpler, so we can just multiply that integral by 2. So we just need to find the area between 0 and 1, basically, and then multiply by 2. So this means that this is approximately equal to 2 times, we'll bring the constant with us here, times the integral from 0 to 1 of all of this. And this is all something we can integrate fairly easily, because this is just a polynomial. We didn't actually do that yet. So dx. So we'll go ahead and plug this in here. Okay. So we get x minus x cubed over 6 plus x to the 5th over 40 minus x to the 7th over 336. And then we're going to plug in x equals 0 to x equals 1. Okay. So we get 2 times 1 over root 2 pi. This is going to be 1 minus 1/6 plus 1/40 minus 1 over 336, and then the rest is going to be 0. So we just got to approximate this, so I'll do it real quick in the calculator here. And we're going to get that this is about 0.663. So if you know, just like from the empirical rule in statistics, or just from working with the normal distribution before, this is actually about 68%, right? So we're getting about 66.3%. So that's not too bad for only 4 terms, okay? Especially because we can't actually get the integral by hand here. So this is a pretty good approximation. It is off a bit, but if we added more terms, then it would work a little bit better. In fact, let's see how much better it would be. Let's just go ahead and add one more term here. I'll just do it in red. So if we added one more term, we'd have what? X to the 8th over, so we're putting in 4. So 2 to the 4th times 4 factorial. So that's 384. And then when we integrate that term, we would have, I'll just write it on the outside here, plus x to the 9th over 384 times 9. Which is 3456. So we're going to add 1 over 3456 to this. Okay, it actually didn't improve it too much here. It just changed it to 0.66. It would still be 3 if you rounded it, but now it's 2.9, whereas before it was 0.6627. So it really didn't change it all that much here. But yeah, so we still get a pretty decent approximation here. The actual value I just threw in the calculator is 0.682 or 0.683. So it's a bit off. It's possible I made an arithmetic error somewhere in here. I don't think so, but it's possible something went wrong. And also, we're not using that many terms. So if we used a lot more terms, it should get closer and closer to that answer. But this is pretty good for an approximation, and it just boils down to just integrating a polynomial, which we can do. It's a whole lot easier than trying to integrate e to the negative x squared.